You are here, so please. So she will be speaking about using a LiDAR to see really what is the wind properties.
The downslope winds.
Yeah. So please.
Good morning, everyone. My name is Ivana Ivancic, and I will be talking about Ligurian downslope winds assessed using LiDAR scanner for the safety management of port area. First of all, I'll explain, I'll give you our user group, give you a bit of a background, explain the goal, explain the LiDAR facility, show you some preliminary scans, and then I'll conclude my presentation with the future work. So our user group is international group, researchers from Croatia, Canada, and Italy. PI of the group is Professor Hrvoje Kozmar from University of Zagreb in Croatia. There are two more group members from Croatia, Professor Branko Grisogono and Dr. Neven Hadžić. Other members are Dr. Đorđe Romanić from McGill University in Canada, and then there is Dr. Alessio Ricci and me from youth. And Dr. Massimiliano Burlando from University of Genoa, who is not the user of the group, but he is managing LiDAR facility in Port of Genoa. So we all know that ports are important for economic development. They serve as hub for international trades. However, they are quite vulnerable to extreme meteorological phenomena, and among all of the meteorological phenomena, wind is one of the most destructive ones, and it can cause accidents in the port area. Here on the video on the left, we can see the port accident due to extreme winds, and on the right is Bora wind in Senj, so downslope winds can also be very destructive. As was mentioned beforehand, most commonly used international codes and standards for assessing loads on the structures due to winds are based on neutrally stratified atmospheric boundary layer, or ABL winds. Those winds can sometimes reach higher velocities near the ground, but those velocities are usually way lower than some other extreme winds. In the past few years, wind engineering community focused on downbursts and tornadoes, but the downslope winds were less explored. So what is downslope wind? It's a very well-known wind in atmospheric sciences. It's known as the wind that blows in lee of high ridges. And all over the globe, it's known by different local names like Alpine Foehn and the Bora, which is one of the most famous ones, at least in Europe. And this wind is, Bora is occurring in coastal Croatia, parts of Italy, and it can disturb port work in Trieste. So in Liguria valleys in Italy, there is specific kind of downslope wind that occurs because cold air is blowing from maritime Alps and Apennines downslope towards the sea area, Mediterranean Sea. So this is driven due to pressure gradient directed from the cold air at the top of the mountains towards the warmer air over the Mediterranean Sea. And where is the pointer? Here, okay. Western part of Genoa here, it's Turkino Valley. Exit of this valley is hotspot for downslope winds during the winter period. So what is the goal of this project? First of all, we want to understand the physics of Ligurian downslope winds and compare Ligurian downslope winds with other winds occurring all over the globe. And second, we want to use those measurements to enhance the codification, so to introduce downslope winds in the international codes and standards. So how are we going to manage that? So we have LiDAR measurements, which will primarily help us understand the physics of downslope winds. And these LiDAR measurements will be used for validation of CFD simulations. CFD simulations are my PhD project, my primarily work. So I'm currently working on simplified geometry. I want to fine-tune all the numerical parameters, so later on I can move to complex built environments. So I'll have buildings, port infrastructure, and orography inside of my domain, so I'll be able to track pressure and load distribution on the port infrastructure, and that will help me to understand actually what is impact of those downslope winds on the port infrastructure. LiDAR facility, first of all, we need to know how LiDAR works. So LiDAR scanner is shooting light into the atmosphere. This light bounces back from moving aerosols in the air and comes back to the scanner. So we have different frequencies. We are shooting light with one frequency into the atmosphere. This light is back scattered from aerosols and come back to the scanner with different frequency. This frequency difference allows us to assess wind speed. And then in Port of Genoa, you can see here is WindCube 400S that is installed at the end of quay, 5 meters above sea level, and it's managed by a research group of University of Genoa. So here are some technical details about WindCube 400S. So maximum range, 14 kilometers. For this project, we used 14 kilometers. Then we have precision of velocity 0.5 meters per second. Physical range resolution can be 75, 100, 150, and 200. And we chose to use 100 meters. Then we have scanning patterns. There are 4 options. So we have PPI. So that means the, elevation is fixed, and then azimuth is changing. It can go from 0 to 360. Then we have RHA, where azimuth is fixed, and then elevation is changing from 0 to 90 degrees. Then is DBS, which is technically LiDAR profiler, so we have vertical profile of the wind speed. And the last one is LOS, so we are shooting just in one direction in the atmosphere. For this project, it was chosen mixed PPI and RHI. Here are azimuthal angles chosen. So azimuth went from 295 degrees to 330 degrees. So as I already told you, here at the exit of Turkino Valley, hotspot for downslope winds. So this triangle is quite appropriate to catch those downslope winds. So measurement campaign lasted from December last year to March this year, and during this period, 6 downslope wind events were noticed. So let me explain a bit those events. So the first 2 events, downslope wind events, were due to cold advection from Scandinavia towards Siberia, so from T1 to T2, and they were paired with low pressure over central Italy. Third event was due to trough that come from northern Atlantic Ocean towards Mediterranean, and it was paired with high pressure over the Balkans. The fourth event was similar to the third one, but the high pressure was stronger, and it was over Scandinavia. In 15th event, downslope winds were due to very wide and very low pressure over Atlantic Ocean paired with high pressure over Central Europe. And the 60th one was the weakest one because it was lower temperature difference between Po Valley and Mediterranean. Here are some preliminary scans. So this negative velocity, negative values are wind is blowing towards the scanner, and we can see that most of the higher velocities are closer to the ground. And this event, I'm showing you 30 minutes of this event. It's the third one, December the 13th, 2024. So what does that mean? So we potentially have a nose shape with downslope winds, which has higher velocities near the ground that can potentially be dangerous for port infrastructure for the lower and medium-high structures. And this nose shape, at least with my experience with CFD, this nose shape is dependent obviously on temperature gradient and on the slope. So I showed you only one event because we still didn't do all the post-processing and data analysis. Because we can see that this potential nose shape could be harmful for port infrastructure. And the future work is obviously post-processing data analysis and then publishing of data set. And using this data for validation of my CFD simulations, where I'll show you now quickly a bit of the work I'm doing. So I said I'm working on simplified geometry. So how did I get this simplified geometry for my work? I had this 3D topography of Genoa municipality. Here is Turkino Valley, my area of interest. I sliced it. I have 10 slices. These black dots, those are those 10 slices profile view, and the red line is this characteristic slope I'm currently working on. So this red line is mountain. This area here, it's representing the sea, and here is inlet, outlet, and my top in this simulation I'm showing you is symmetry. So at the inlet I have wind blowing inside with velocity of 10 meters per second, and this wind has a temperature gradient. So temperature is decreasing with the height by the coefficient dt. In this case, I will show you where dt is 4 kelvins. So here are the results. So we can see that I managed to develop this nose shape. Obviously, I'm working with runs. I'm running, I forgot to tell you, I'm working with an open foam. So I'm running runs. So it's not time dependent, which is one mistake I'm working with knowingly. Then I'm not working with, I still don't have exchange of temperature between the atmosphere and the ground. That's another mistake I'm aware of. And I'm using Boussinesq approximation. So density, change of density due to temperature is insignificant in this case, only when we are multiplying it with the G. So that's all from me. Thank you for your attention.
If there are any questions, we have time. This time. That's the question. Okay. It was a very nice presentation.
Thank you.
So thanks. So Felix Nieto will be the next presenter. And is it about something we already seen in the presentation of Bernard with the solar panel survey?
Okay. So thank you very much, Olivier, for the very kind presentation. Thank you. So, okay, so think. Okay.
And your name?
Felix Nieto, this one. Okay, that's fine. Okay, thank you. Thank you very much. Let's start then. So, yes, what I'm going to present here today is a piece of the work that we have been doing under the project whose name is ERIES Solar, that represents the collaboration of the University of Coruña from Spain, University of Zagreb from Croatia, the Von Karman Institute from Belgium, and Western University, which was the host facility for this project. So the outline of the presentation is this. Let's start with a very brief introduction. Then I'm going to explain a little bit the scope of the tests that we are doing. And in terms of results, I'm going to focus on two main points. First, the downburst flow characterization, and then some pressure coefficient distribution over the solar panels that we have obtained. So I would like to mention that we have a huge amount of data, and that we are now still in a preliminary analysis of the results. So the motivation for this project, I think it's important to understand that I think that we all agree that nowadays the non-synoptic wind actions is the frontier in knowledge that we have to address. And ERIES Solar aims to address that frontier, mainly focusing on the effect on solar trackers or solar panels. We have considered 3 different types of non-synoptic winds, which are tornadoes, bora wind, and downbursts. And in this presentation, I'm going to focus only on the downburst results that we have obtained. So eventually, what we are aiming at is to obtain some description of the loads associated with downburst actions that can be translated into codes of practice and structural recommendations. So obviously, after Girma's presentation and also Federico's presentation, what can I say about the downburst? So just the definition: as an intense, localized downdrafts produced by convective storms. And what I think it's important for this application is that the size range between 1 kilometer up to 10 kilometers in diameter. So essentially what we have is this descending cold air that impinges on the ground, deflects, and then there is a primary annular vortex that is then moving over the surface, this kind of donuts that Girma mentioned it before. So I put some attention on the size of the downburst because for solar panels, we also have to understand that the size of typical solar farms may be ranging from something small, just around 0.2 square kilometers, up to, for instance, around 50 kilometers for the larger ones. So that means that the downburst can cover, if not all, at least a very substantial part of the solar farm. So obviously, these are typically not urban environments, so there is no risk for life typically, but the economical impact for developers can be really substantial. So this is something that, from that perspective, it's very interesting to address. So this is just a picture of the team, or at least a part of the team, when we were doing the first tests in September last year. And just very briefly, just to comment about the facility, that obviously windy at Western can generate this kind of scaled downburst. And in this case, we were, for the results that I am going to present here, we are considering impinging jet velocity of 8.6 meters per second, obviously at lab scale, although we have also tested some other different intensities. So this is a scheme of the facility. So essentially, there are here 6 large fans, which are the ones that generate here a very strong pressure. So eventually the louver here is opening, and with the release of the pressurized flow, we have the jet impinging on the floor of the wind tunnel. And obviously this is out of scale. Here we have the 6 rows of solar panels that we wanted to test. In terms of instrumentation, the characterization of the flow associated with the downburst has been made by means of a rack of Cobra probes. We were considering 8 different Cobra probes that were located at different heights in order to have the profile of the flow, with a high frequency sampling rate of 1.25 kilohertz. Also, the rack of Cobra probes was placed in different positions in the radial direction. So this is pretty much a scheme where here you have the axis of the downburst, and this should be the location of the solar panels. So this the angle is related to the reference direction here, and also the distance. We will see that is also relative to the diameter of the louver that we were considering for generating the jet. The model that was tested was this 6 rows of the array of solar panels, solar trackers, and a geometric scale of 1 to 20. So each row has a length of around 1 meter with a core width of 10 centimeters, and the distance to the ground is of 5 centimeters. So it's important to take into account that each row was instrumented by means of 12 different rows with 8 pressure probes each. So that means that in total we have 576 pressure taps requiring 18 scanners of 32 pressure ports each, which obviously was quite a complex endeavor. So for the characterization of the flow, some of the preliminary results that we have obtained was just by means of getting the ensemble average of several repetitions of the different tests, in concrete 8 experimental repetitions that were done. And over that ensemble average, we also obtained a mobile mean in order to have a description of the flow. And over those results, we also obtained the PDFs, the Morlet wavelets, and the frequency of spectra. Just to show some results, this is one of the cases. For instance, for a Cobra probe located at 15 centimeters over the ground. So essentially what we have here is the ensemble average of the 8 repetitions and also the moving mean that is kind of averaging obviously the oscillations in the flow. What we obtain obviously is the strong increment in the velocity and then a subsequent decay with mainly a plateau here as is described in the literature. So for the increment of time of the moving window for the time average was relatively high, 0.4 seconds. So that means that we did not really have a lot of resolution in time. So for instance, the Morlet wavelet identifies, higher energy associated with the peak in the flow, but with not really a very in-depth resolution in terms of frequency. And this is just another example, a little bit farther away along the radial distance with similar results. So more recently, we were studying a little bit the sensitivity of the results depending on the size of the time window for the time average. So we considered the window size of 0.1 seconds, 0.2 or 0.5, and these are the results that we obtained, for instance, for the radial component. Obviously, the shorter time window, the better resolution in time, but with the general characteristics of what you are expecting from this kind of downburst flow. In the previous slide, just the naked eye didn't really show, cannot really appreciate, huge difference in that regard. So here, what I am plotting is just the peak velocity at different heights depending on the size of the time window. And here we can observe that pretty much the shape of the nose profile is similar, but the difference on the results that you can obtain for the peak velocity, depending on the size of the time window, change up to 10%, okay, with values, maximum values a little bit higher than 10 meters per second, up to a little bit higher than 9 meters per second. So that is the effect of the resolution of the time window that we wanted really to understand. Let's move now to some perhaps more practical results that are related with the pressure coefficients on the solar panels when the downburst arrive. So just some, let's say, notation here. The downburst is coming, let's say, from the left. And here we have the 6 rows of panels. So the naming convention is that the panels are named as 1, 2, 3, 4, and so on as they are farther away from the jet. And this is the distribution of the pressure probes over the panels, where you have to also understand that in these points here we have really 2 pressure probes, one on the top side, another on the lower side of the panel. So a first idea of results are these net pressure coefficients that have been obtained for just one realization. So here you have in the first row the results for panel 1, which is the one that is the closer to the jet. And as you can see here, we are considering two different tilt angles for the panels. So the sign convention here is that positive tilt angles are nose up, negative tilt angles are nose down. So that means that this scheme corresponds to plus 30 degrees. And if you have the nose in the lower part, that should be the minus 30 degree angle of attack. Okay. So for the minus 30 degree angle of attack case, which is nose down, we are finding quite a strong net positive pressure for panel 1, which is the closer to the jet. And for instance, for panel 4, we can see that there is a different story, let's say, with not a strong peak here at the very beginning in time, but more like a plateau with obviously some oscillations that we still have to understand if these are associated with real interference between panels or these are the vortices associated with the downburst. For the positive tilt angle, here the situation is different in terms that the sign of the net pressure is changed. In this case, this is negative since the suction is having the main role here. And also there are some differences here in behavior. So for the panel 1, we have here the peak at the very beginning when the downdraft arrives. It's not the case, for instance, for panel 4, where we have higher values for later times. And these are just the maps of the pressure coefficients. So these are the peaks that have been obtained applying the peaks over threshold method, as suggested by ASE. So these are for the minus 30 degree tilt angle. This is maximum CP and minimum CP on the top side of the panels. So there is an obvious difference between panel 1 that is mainly receiving the downburst and the other ones that are in the wake, so to say. For the same case, minus 30 degree angle of attack, so panel nose down, for the bottom sides of the panel, these are the results that we are obtaining for maximum pressure coefficient and minimum pressure coefficient. In this case, you can see here this strong negative pressure, mainly in the corners of the panels that are farther away. And these are the values for the net pressures. And just to finish, for the plus 30 degree angle of attack case, maximum pressure and obviously the minimum pressure, since we have suctions. So you can see how there is an obvious interference between some panels of the others with higher negative pressure here for panel number 6. And these are the net pressures that tell you quite a similar story. And just to finish, just to conclude, so we are at the very beginning, but we are increasing the understanding that we have about how the downbursts can be impacting these solar panels, finding that, of course, there is a strong loading on the panels associated with the downburst, but we also have to dive a little bit deeper into the results in order to understand the potential interference between one panels and the others. And I think this is all for now. Thank you very much. And sorry if I am a little bit...
Thank you, Felix. Are there any questions? Yes, please.
Do you plan also to compare the fact due to synoptic wind or just downwards?
Thank you. That's a very, very interesting question. Yes, we did some tests also considering AVL standard conditions. And yes, we would like also to check, but I think that without doing spoilers, that is also very much related with the study that was done for Bora wind that is going to present later Petar, that perhaps can also provide a more general frame for the question, but of course, it's very, very convenient really to check both things and see what is.
While recording and then streaming into the sound is like this, you know.
Okay, sorry.
someone who wants to be asking something, talk to the microphone, not for the room. Because we are recording in stream, so if people want still.
Okay, thank you. Good to know. So yes, obviously it was very. It's very convenient to really compare, because that is also very important for the industry to really understand how they are, if they are or not in the safe side for wind loading.
Okay. Thank you very much.
Okay. Thank you.
So the next presentation given by Federica. She has a strong voice.
Yes.
So she doesn't need.
Okay, so thank you. Good morning, everybody. Today I will present ERIES project TLTB, thunderstorm loading on tall buildings. And first of all, I would like to acknowledge the contribution of all the authors of the paper, in particular of Stefano Torre and Edoardo Ruffini from Nova Fluid Mechanics, who performed the experimental tests, and also of Camila Aldereguya Sanchez, who is a PhD student of University of Genova, who elaborated all the results as a part of her doctoral project. So I think I could skip this slide, since you saw these pictures many times already this morning. European wind climate is dominated by extratropical cyclones and by thunderstorms, which are very frequent events, especially at mid-latitudes. And statistical analysis of extreme wind speed in mixed climate areas that are frequently struck by thunderstorm have shown that high return wind speeds are always related to thunderstorms. So thunderstorms in some cases may produce a downburst, which is a downdraft wind which impacts the Earth's surface and generates strong radial velocities, especially at heights around 50 to 100 meters above the ground. Thunderstorms are characterized by properties which are different from synoptic events, since they have a typical nose-shaped wind profile, and they have non-stationary character over time intervals between 10 minutes and 1 hour. Actually, the codes normally adopt synoptic wind models for defining wind actions on buildings, which is characterized by a profile which, a mean wind profile with a velocity which increases with the height above the ground, and stationary characteristics. So normally high-rise buildings do not suffer damage from thunderstorm downbursts. However, we can ask ourselves whether the wind actions evaluated by codes are correct in order to design these structures. And so the objective of the project is to answer a question which was posed by Nova Fluid Mechanics, which is a wind engineering consultancy. And the question is whether in a mixed climate area where design wind speeds from synoptic and thunderstorm events are comparable, the current procedure to derive wind loads on tall buildings is suitable, or if a specialist analysis of thunderstorm would maybe change the design of tall buildings. So the project is divided into two main steps. The first one is the design of a simple and low-cost device in order to reproduce the typical nose-shape profile of thunderstorm winds. And this could represent an economic alternative that could be used also for commercial projects, to more sophisticated methods that are used, such as impinging jet techniques that are used at Windy Dome at Western, or multiple fall wind tunnels. And then after this, the project has been, during the project, experimental tests in the wind tunnel have been carried out with both nose-shaped and synoptic profiles in order to evaluate pressures and forces on buildings. In particular, two buildings have been tested, the benchmark arc building and a real building which is under construction, which was analyzed by Nova Fluid Mechanics. It will be called Project X for confidentiality. And the building is located in a thunderstorm-prone area, and it will be equipped with a monitoring system when it will be finished, and so it will be very interesting to compare the results from wind tunnel tests with full-scale measurements. So the project is organized in these 4 steps. At first, we simulated nose-shape profiled in the wind tunnel with this passive device. Then we designed the models and we built the models of the buildings. We performed wind tunnel tests. We analyzed the preliminarily analyzed results, and then the last phase of the project is the design and construction of an active grid and performing new wind tunnel tests in order to compare the results with an active grid with the passive grid. And this part of the project is still ongoing. So tests have been carried out at the Giovanni Solari boundary layer wind tunnel at University of Genova in the last part of our working section where boundary layer tests are performed. In order to develop a boundary layer, we use the traditional devices such as roughness blocks on the floor of the wind tunnel, fences and spires at the inlet. And in addition to this, we designed a specific device that we call thunderstorm grid, which we located 4 meters from the inlet, and it is constituted of modules which span the width of the wind tunnel and have openings of different size. And the main objective of these modules is to slow down the velocity at the top of the wind tunnel in order to create the nose-shaped profile. So we perform tests with many configurations of both traditional and the new passive grid device, and we found that the main parameter affecting the height of the nose of our profile is the distance between the lowest module of the grid and the floor of the wind tunnel. This figure shows the height of the nose as a function of that distance, and we can see that we were able to achieve heights of the nose in full scale in the range between 50 and 150 meters. Just as an example, here we can see the profiles that we obtain for a height of the nose of 100 meters in terms of velocity and turbulence intensity. And this picture shows that the power spectral density functions of turbulent fluctuations fit well the von Karman spectrum. The second phase is model testing and construction. So we tested the Kark benchmark model at a geometric scale of 1 to 400. And we perform both high-frequency force balance and high-frequency pressure integration tests. For the force balance test, we built a rigid model by the use of a carbon fiber sting, and the model was built using high-density polymeric foam, while pressure integration model was 3D printed, and it was equipped with 280 pressure taps. Project X model and Kark building was tested in isolation, while Project X model was tested at a geometry scale of 1 to 300, only using high-frequency pressure integrations. It was, again, 3D printed. We used 365 pressure taps located along the surfaces and concentrated in the corners. And we tested the building by reproducing also the surrounding area with a radius around the building of around 240 meters in full scale. So tests on the Kark benchmark model were carried out using 5 different configurations. 3 of them were for low turbulence intensity, 1 synoptic and 2 thunderstorm profiles with 2 different heights of the nose, and 2 high turbulence intensity profile, 1 synoptic and 1 thunderstorm. Due to symmetry, we tested only 19 wind directions with 10-degree increments. While Project X was tested only with 2 different profiles corresponding to high turbulence and for 36 wind directions with 10-degree increments. So these are some preliminary results concerning the mean pressure coefficients on the windward face of the Kark building in the 5 configurations. And we can see that maximum pressures, maximum mean pressure coefficients, are located at heights that depend on the profile that we consider. In particular, we have maximum pressure close to the top for synoptic and at lower heights for thunderstorm profiles. And we have lower pressure, mean pressure coefficients if we increase the turbulence intensity. This is just another elaboration of results showing the power spectral density functions of the base forces measured under this configuration, so 0-degree angle of attack. In this case, Fx is the along wind force and Fy is the crosswind force. And we can clearly see peaks in the spectra related to vortex shedding, which are much more evident and spiky for the synoptic wind configuration. This is a very, very short summary of some results for the Project X model. Okay. In this case, the study started with statistical analysis of wind measurements in a location, in an airport close to the location where the building is built, by separating synoptic and thunderstorms, and from this distribution we obtained also the mixed distribution by combination. And we can see that for 50-year return period, thunderstorms are dominating the local climate. We performed analysis considering 3 different conditions, so thunderstorm, synoptic, and mixed analysis. And this figure plots the peak dynamic base loads in the X and Y direction, so along the 2 main axes of the building, on varying the angle of attack of the wind. And we can see that mixed analysis strongly overestimate the loading on the building, while synoptic and thunderstorm provide quite comparable results. But synoptic provides larger values for all wind directions, even if the design velocity at 10 meters for synoptic is lower. And we think that this difference may be due to the different turbulence intensity that we used in the 2 tests. So just to conclude, we think that the passive grid that we designed is a practical solution for the experimental simulation of nose-shaped profile. And we found that in some cases, thunderstorms can generate higher pressures at lowest level, and this can be important for the design of the cladding of high-rise buildings, while in the case of the real project that we analyzed, I think that the results that we obtain highlight the necessity of distinguishing between the two different loading conditions provided by synoptic and thunderstorm events. As I said before, actually the project did not finish yet, so the active grid has been designed and it has been built. It is already in our laboratory, but we still have to install it in the wind tunnel and to perform the tests. So we will perform the tests, trying to reproduce also the non-stationary character of the thunderstorm and to compare these results with the ones that we obtained with the passive grid. So that's all from my side. So I thank you for your attention. And
Are there any questions? No? If not, we are just late by 10 minutes. So we'll be late to the lunch, but I think it's acceptable for all of you. So the next presentation and last one is by Peter. And thank you again.
thank you.
So thank you very much for the introduction. I'm lucky here because I am continuing with the ERIES solar project, which already has been talked about by Felix here. So I'm Petar Škvorc. We have here a collaboration between Spain, Canada, Belgium, and Croatia. And I will tell you something about experimental modeling of gusty Bora windstorms. So, as already has been mentioned a bit by Ivana, Bora is a non-synoptic gusty wind which appears mostly in coastal Croatia. Now, it has mean velocities of 20 meters per second, which is already a relatively high velocity. However, the gust velocity goes up to 100 meters per second, which is, of course, very dangerous. And it can also be very harmful to traffic, to agriculture, to infrastructure, and so on. It is most common in winter, but can happen anytime, and also has pulsation periods from 3 to 11 minutes, which is also quite long for over 100 meters velocity. Now, even though Bora is confined to Croatia, there are some similar winds around the world, such like Santa Ana in California, Chinook in North America also. Then we have Zonda in South America and Fen in Europe, so there are similar winds around the globe. Now, our goal here was to experimentally simulate this gusty Bora wind at the Windy Dome facility at the Western University in London, Canada, already mentioned by Girma and Felix. And now, given that this is a part of ERIES Solar, so our idea was to also simulate Bora wind on solar panels, but the first issue we run into is how do we even simulate Bora wind? So as mentioned before by Dr. Girma, Windy Dome, it can simulate mostly for tornadoes and downbursts, hexagonal shape over 100 fans with a 60 fan wall right here, which is mostly used for simulating straight flows. There's also an upper chamber. This upper chamber here can produce positive or negative pressures, and with that it can simulate tornadoes or downbursts. There is variable frequency drive on all the fans in the lower chamber, which is very important for us, so we can modify the velocities in real time. And of course, surface roughness elements can be used as well as vortex generators and contraction to increase the flow velocity. So in order to simulate Bora wind, which hasn't really been done in wind tunnels before, we had to devise some new methods. So first one is the generic flow simulation. We selected two velocities, a base velocity and a gust velocity, so a lower and a higher velocity, and we alternate between them at a certain time period. And the second method, we did a prototype simulation. We have some velocity measurements taken at full scale on a meteorological mast, and we can replicate them in the wind tunnel or in the Windy Dome using the variable frequency drive. And then the last method that we used is the concurrent straight flow and downburst simulation. So we can have concurrent straight flow from the 60 fan wall in the windy, and we can then combine this with the downburst simulation. As far as the flow measurement goes, we have Cobra probes. Felix already mentioned 8 of them. They have at various heights, and they have a 1.25 kilohertz sampling frequency, and this is what we used for our flow measurement. So I'll show you a bit of the results that we get from the 3 different methods that we use. So starting with the generic flow simulation, we picked two velocities, a base velocity, lower velocity, and then a gust velocity and higher velocity. And we simulate lower velocities and higher velocities for a certain time period, and we alternate between them by changing the RPMs of the fans. Now here we are limited by the acceleration of the fans, so we can only go 5% of nominal RPM per second, so this is basically what defines the slope. With this we are trying to reproduce the gustiness of Bora wind. Now if we use surface roughness elements, this is the lower diagram here, we get much more turbulence in the flow, as evident here by the very turbulent nature of the mostly the gust winds, but also with the base winds as well. This also impacts slightly our mean velocity, so if we introduce surface roughness elements, we have a bit of a lower velocity, lower mean velocity. On this we can do a continuous wavelet transform using more wavelets this time. And we can see here that higher energy content is in the higher frequencies in the case of increased turbulence here. As we can see here, corresponding to the higher velocities, also higher turbulence appears here as in brighter colors, showing more turbulence, more energy content in these gusty velocity conditions. If we do a probability density function here, so this basically shows us for a random period in time, a random point in time, what is the probability the velocity will fall inside a certain range. For the low turbulence flow, we have 2 very strong pronounced peaks at the base and gust velocities, as we would expect. When we increase the turbulence via surface roughness elements, we have much more evenly spaced out probability density functions, as expected due to the increased turbulence. Now the second method that we use is the prototype simulation. So as I mentioned, we have full-scale measurements from a meteorological mast located in the town of Senj in Croatia. We have a time record for 7 days in total with a sampling frequency of 4 Hz, so real-world data. Here is one section of it for 1 hour length. If I put all 7 days in there, we cannot really see anything. So from a 1 hour section, these are the real results from the Bora, and here we can see going up to almost 35 meters per second and down to 5 meters per second, so we can see this gustiness of Bora. Now if we take these measurements and we perform a moving average on it, we also know that 100% RPM or 100% variable frequency drive in the windy dome on the 60 fan wall corresponds to 30 meters per second velocity. Taking a moving mean of the real world data and translating that in the variable frequency drive, we can get here black points showing us how we are modifying the RPMs basically of the fans in the windy dome. And the red line here shows us what we measure with the Cobras. So we can see almost a perfect correlation between the VFD, variable frequency drive, with the mean velocities that we're getting in the wind tunnel. There's a slight offset in time, simply because the fans are on one position and the Cobras are far away from the fans, so we have a certain offset here. If we do a PFD, a probability density function of this is a full scale, so taken from the meteorological mast, and here's what we get in the windy dome. We can see the shape is roughly there. We have a bit of a bulge here in the simulated PDF, but this is mostly due to the fact that we can only take a few minutes of the full-scale velocities to reproduce in the windy dome. So if we had perhaps taken a different section from the full scale, maybe we would get a bit of a different shape here for the PDF. But the important thing for us here is that we are actually managing to reproduce the shape from the full-scale Bora. And then the last method that we use is the concurrent straight flow and downburst simulation. So at this point, I think everyone knows what a downburst is. So we have this strong downward jet, we have this strong gust then in the radial direction. If we put our measurement equipment, our Cobras, far away from the jet location, we can get the predominantly horizontal wind velocity. And this is what we can see here in the time history. We have some base velocity that we are producing here with the 60 fan wall. And then when the jet impinges on the cobras, we have this really, really strong gust, and everything else is similar to as it appears for the downburst simulations. But what we are interested in here is this gust, because this is the strongest gust that we can simulate. Again, if we do a continuous fluid transform on this, we can see here that there is a very strong energy content at very low frequencies corresponding exactly to the locations when, to the time period when the impact jet is directly on the cobras. And this is something that we expected, and this is something that we want to show also for the Bora wind. So to conclude, in those three different methods that we used, they all have some advantages and some limitations. So for the generic flow simulation, the advantage is that this can be performed in several laboratories around the world. All that we need is to be able to change from the base to gust velocities. Now, of course, the limitation here is that it doesn't really capture the stochastic nature of Bora in the sense of Bora doesn't only have base velocities and gust velocities, but also everything in between as well. Now, for the prototype simulation, this can give us the most accurate simulation in terms of the mean velocities of Bora. However, several limitations here that, first of all, we need to have the full-scale data available for us, which is not really something that is very common. We can only simulate a short time frame comparing to the full-scale Bora, of course, because Bora can blow for days and days. We cannot really do that in the wind tunnels. And this requires the variable frequency drive, because we need to really have the ability to fine-tune the RPM of the fans to actually reproduce the moving mean that we can get from the full scale. And then, as far as the concurrent straight flow and downburst simulation goes, this simulates the strongest possible gust that we can get. However, we can only simulate one gust at a time, and of course this can only be done in facilities that can generate downburst flows, which is also very few. Now, Windy Dome here is unique in the sense that it can do all three of those simulations. Now, with the combination of all those three methods, we can yield quite accurate simulations of Bora wind. And this, of course, then shows that Windy Dome has these capabilities other than all the other non-synoptic winds that it can produce. And this here is a visualization of the downburst flow as performed in Windy. There you go. So as I said, this is a part of the ERIES solar research that we're doing here as a combination, as a collaboration between Croatia, Canada, Spain, and Belgium. So thank you very much.
Well, thank you, Peter. Are there any questions to the audience? So, thank you very much. I must complete by an advertising. So there are two presentations this morning that are competing, the one from Peter and the one from Ivana, that are competing for the Young Researcher Prize. So please have a special view on this presentation after they are done, of course. And if you don't know, many of the presentations that are given here will be also not given the same way, but a different way in the European and African Conference of Wind Engineering that will be held in Trondheim, Norway in June. And we organized, Maria Pia is one of the organizers of a special symposium for the ERIES project. So many of the things that are presented here will be presented more completely at this occasion. And now it's time for lunch, except that we have first an announcement.
Just to complement the information I gave you before, so the